In section 4.2, we're going to be finding areas in the plane using very ancient techniques of approximation. Unfortunately, this is going to involve adding up long lists of numbers. So as a warm-up, let me show you a notation which can be used to kind of condense the way of writing long lists of numbers. And this is called sigma notation. So first of all, sigma refers to the Greek letter that looks like that. That, by the way, is a capital sigma. A lowercase sigma looks like that. We might be using that a little bit later on in calculus. But here we're going to be using the capital letter sigma. Now let me show you what an example of sigma notation looks like. I'll write it down and then I'll tell you how to interpret it. So this notation would be read as the sum as k goes from 2 to 4 of 2k squared minus 3k plus 1. This letter k is known as the index of summation. And the way you interpret it is this way. I'm going to take the number k equals 2 and substitute this into the expression. That's going to give me a number. Then I'm going to go up by integer values. Next, I'll plug in k equals 3. And then I'll plug in k equals 4. And when I get to k equals 4, I stop, because this number on the top says where to stop. So sum k equals 2 to 4 means I plug in k equals 2, and then 3, and then 4, and stop. So when k equals 2, and I substitute into this expression, I get 2 times 2 squared minus 3 times 2 plus 1. When I plug in k equals 3, I have 2 times 3 squared minus 3 times 3 plus 1. And when I plug in k equals 4, I have 2 times 4 squared minus 3 times 4 plus 1. Let's simplify each one of those. In the first one, I have 8 minus 6 plus 1, which is 3. In the second, I have 18 minus 9 plus 1, which is 10. And in the third one, I have 16 times 2 is 32 minus 12 plus 1, which is 21. And then 3 plus 10 plus 21 is 34. For a second example, let's look at the sum I equals 1 to 4 of I minus 1 squared plus I plus 1 squared. Now, if you think you understand how this is working, you might want to pause the video and try this out on your own. Otherwise, keep watching. Here, my index of summation is I rather than k. But I'm going to take I equals 1, 2, 3, and 4, substitute into this expression, and then add the results. So I'll have 1 with I equals 1. Then I'll substitute in I equals 2. And then I equals 3. And then finally I equals 4. So first let's plug in I equals 1. 1 minus 1 is 0 squared plus 1 plus 1 is 1 squared. 0 squared plus 1 squared is 1. Next I plug in I equals 2. 2 minus 1 is 1 squared plus, plugging I equals 2 here, that's 3 squared. 1 squared and 3 squared is 10. Next I plug in I equals 3. I get 2 squared plus 3 plus 1 is 4. 4 squared. 16 and 4 is 20. And then finally, I plug in I equals 4. 4 minus 1 squared is 3 squared. And 4 plus 1 squared is 5 squared. And 9 plus 25 is 34. And it is up. Oh, drat, I've made a mistake. Notice back here, wow, you've probably been watching this the whole time. When I plug in I equals 1, this is a 2 squared, not a 1 squared. Sorry about that. This is actually 4 here. This is one of those times that you would have corrected me in class before I got so far along. Well, let's take 4 plus 10 plus 20 plus 34. That's 64 plus 4 is 68. So finally, let's do one more example. This one's going to look a little bit funny, but I want to make sure you know how to interpret it. Let's take the sum I equals 1 to 5 of 7. Well, what makes this look weird is that we don't see any i's in this formula. But still, when I equals 1, I get a 7. When I equals 2, still get a 7. When I equals 3, I get a 7. When I equals 4, another. And when I equals 5, I get a fifth 7. So as I goes from 1 to 5, I get 7, 7, 7, 7, 7. And the sum is 35.